Hello and welcome to my YouTube channel. So in this video, I'll be discussing on the quantum numbers, a very popular and important topic in chemistry. But before we move on, if you are yet to subscribe to this YouTube channel, do well to click the subscription button, click the notification bell also so that you can receive notifications whenever I drop subsequent videos like this that can help to improve your performance in chemistry and science. So let's move directly to what we have for today, quantum numbers. So what exactly are quantum numbers? Now, quantum numbers are simply sets of numbers that are used to describe the state of an electron in an atom. So we understand that atoms are made up of different subatomic particles, the proton, the neutron, and the electron. And specifically, the electron are located on orbitals where they revolve around the nucleus of the atom. So now the set of numbers that are used to describe the state of these electrons in their orbitals, even as they are contained within an atom, is what we refer to as quantum numbers. So, which simply means that they help to explain the state of an electron in their orbitals. So, basically, each electron in an atom is described by four quantum numbers. So, to put, we have four types of quantum numbers. And let's list them. The first is the principal quantum number. The second is the azimuthal quantum number. The third is the magnetic quantum number. And the fourth is the spin quantum number. So these four types or sets of quantum number are what we use to describe the state of an electron in an atom. So just to give an overview, the principal quantum number helps to determine what we refer to as the energy level, while the azimuthal quantum number helps to describe the shape of orbital, that is the orbital where the electron is contained now. And then the magnetic quantum number helps to describe the orientation of the orbital. And then lastly, the spin quantum number helps to determine the electron spin, that is the spin direction of the electrons. So let's go more in the details of these four quantum numbers. So we'll start with the first quantum number, which is the principal quantum number. So what is the principal quantum number? Now the principal quantum number, just like I mentioned earlier, is the quantum number that helps to determine the energy level in which an electron belongs to. From the Neil Bohr's model of an atom, you understand that electrons are in quantized orbitals, also known as energy levels. So it is the principal quantum number now that helps to determine the energy level of the electron. And then this energy level now is denoted by N. So which means N can be equal to 1, 2, 3, 4, 5, and so on, as the case may be. And each of these energy levels now are also denoted by specific letters. So when n is equal to 1, we have the energy level to be K. When n is equal to 2, we have the energy level to be L. When n is equal to 3, we have the energy level to be M. When n is equal to 4, we have the energy level to be N. And when n is equal to 5, we have the energy level to be O. So that is K, L, M, N, O. Those are familiar alphabets in English. So these are used to denote or describe the various energy levels that we have within an atom. So these energy levels also helps us to determine what we refer to as the number of shells in an atom. So with the knowledge of the principal quantum number, we are able to determine the number of shells that are contained within an atom. So that is simply what the principal quantum number is all about. So from the principal quantum number, you can also get to calculate the maximum number of electrons in a shell. Maximum number of electrons in a shell, which is usually equal to 2n square, where n now, like we said earlier, is the energy level or the number of shells. Very simple and straightforward. Now, without wasting time, we'll move to the second quantum number, which is the azimuthal quantum number. Now, the azimuthal quantum number, which is usually denoted by letter L, as in small l now, also helps to determine certain characteristics and states concerning the electron. Now, number one, this includes the uh, shape of the orbital. Now, in this case, now the orbital that is containing the electron. We understand that orbitals are regions where electrons can be found within an atom. That should be already clear from the models of an atom. If you are yet to watch the video, you can check my previous videos on that. So this azimuthal quantum number helps us to determine the shape of the orbital where the electron is found. That is the first thing that we can determine from the azimuthal quantum number. Also, the azimuthal quantum number helps us to determine the number of subshells. So we established the principal quantum number that atoms are actually made up of shells. But we also know that these shells are further divided into subshells. So the azimuthal quantum number helps us to determine the number of subshells within a shell. And then lastly, the azimuthal quantum number helps us to determine the angular momentum of an electron. The angular momentum of an electron. Now, what do we mean by angular momentum? Angular momentum, from the knowledge of physics, classical physics now, is simply the when we say momentum, of course, we understand that it's referring to the change in what? In speed. And then angular momentum now is the change in speed of the electrons now, even as they move on their orbitals. You understand that the orbitals are not completely spherical and they differ in shape. Just like we said, the azimuthal quantum number helps us to determine the shape of the orbital. So the angular momentum of the electron now describes how the electrons move on their orbitals and how fast they move, as in the speed now, how fast they move on their orbitals. So let's see and dive into this. When we have various values for L, you have to understand that the values for L, which is the azimuthal quantum number, ranges from 0 to n minus 1, which means to determine the azimuthal quantum number, it can range from 0 to n minus 1. Now let's see how these numbers helps to determine these various things that we have aforementioned. Now when our L is equal to 0, that means that the shape of the orbital is spherical. When our L is equal to 1, that means the shape of the orbital is dumbbell. When our L is 2, the shape of the orbital is double dumbbell. And then when our L is equal to 3, the shape of the orbital is complex. So this gives us an idea of the shapes of the different orbitals. This from the understanding of quantum atomic structure, where we understood that orbitals are not completely circular or spherical in shape. It differs based on the proximity from the nucleus. And also, based on the different shells that we have now, we are also able to determine the number of subshells from the azimuthal quantum number. So which means when we have n to be equal to 1, we said the azimuthal quantum number ranges from 0 to n minus 1. So when n is equal to 1, that simply means that L will be equal to 0. So it means that the first shell, which is the first energy level of an atom, has just one sub shell. And then when n is equal to 2, then L will be equal to 0, 1. Said it ranges from 0 to n minus 1. So n minus 1 now in this case will be 2 minus 1, and that is 1. So that means the second energy level or the second shell in an atom has 2 sub shells. And then of course when n is equal to 3, L will be equal to 0, 1, 2, which is the n minus 1 in this case, which means the third energy level or the third shell in an atom is made up of 3 sub shells. So this is how we are able to determine the number of subshells from the azimuthal quantum number. So the one subshell rather in the first energy level or the first shell now is the 1s. I'm already relating this now with electronic configuration. So 1 here is showing the principal quantum number n equal to 1, and then the s is showing the what? The spherical orbital of the azimuthal quantum number. For spherical orbital, it is denoted by S, dumbbell is denoted by P, double dumbbell is denoted by D, and then complex is denoted by F. So that means in the case of the two subshells now, the two subshells that will be contained will be 2s, 2p. That's in the second energy level. So the 2 is showing second energy level, which is n equal to 2. And then the s and the p, respectively, is showing the subshells L equal to 0 and subshell L equal to 1, respectively. And then for the third energy level, n equal to 3, the three subshells present now will be the 3s, 3p, 3d, showing 3 indicating the third energy level, and then SPD indicating L equal to 0, 1, and 2, respectively. I want to believe this is clear and well understood. Now, without wasting time, let's move to the next quantum number, which is the magnetic quantum number. So the magnetic quantum number which is usually denoted by m subscript l, also helps us to determine certain characteristics or states of electrons. Now, number one, it helps us to determine the orientation in space of orbitals. Number two, it helps us to determine the degeneracy, also known as multiplicity of orbitals. Now, let me explain what this means, because these 2 points are actually interconnected: orientation in space of orbitals and the degeneracy or multiplicity of orbitals. Now, you have to understand that the values of the magnetic quantum number ml ranges from minus L to plus L. So which means we can directly determine the magnetic quantum number from the value of the azimuthal quantum number. And from this now, we are able to determine the degeneracy or the multiplicity of that orbital. What we mean by degeneracy now, when you hear degenerate orbitals, that means orbitals that are on the same energy level. So they belong to the same subshell, but then there are various orbitals, degenerate orbitals now, that are all lying on the same subshell or energy level. So that means, take for example, when L is equal to 1, or let's start from 0, when L is equal to 0, which is the uh, azimuthal quantum number denoted by S, if you remember, then when L is equal to 0, that means we are going to have M subscript L to be equal to what? 0, right? Because it ranges from minus L to plus L. So that will be minus 0, 0, plus 0. That is still 0, right? So which means for the S L equal to 0, which is the S azimuthal quantum number, it has just one orbital within that subshell, right? But when L is equal to 1, let's see. So in that case now, our ML, which gives us the degeneracy of that subshell or orbital, will now be what? Minus 1, 0, plus 1. So that means in the subshell L equal to 1, which is subshell P, there are what? There are 3 degenerate orbitals that makes up the subshell. So we have degenerate orbital denoted by minus 1, 0, and plus 1. That's 3 degenerate orbitals. Now, in the case where L is equal to 2, so that means let's see the number of degenerate orbitals that we are going to have. So we have ML equal to minus 2, minus 1, 0, plus 1, plus 2. So that gives us what? 5 degenerate orbitals. Now also, another thing we can determine from the magnetic quantum number is the splitting of spectral lines in magnetic field. And this is actually where this quantum number got its name from. So the magnetic quantum number can also be used to determine the splitting of spectral lines in magnetic field. And this phenomenon is actually referred to as the Zeeman effect. So we have the Zeeman effect, which is the phenomenon whereby spectral lines splits in the magnetic field. So this can also be explained with the magnetic quantum number. The last quantum number, which is the spin quantum number. So The spin quantum number simply helps us to determine the spin direction. The spin quantum number simply helps us to determine the spin direction of an electron, and this is the uh, quantum number that helps to differentiate electrons that are found within the same orbital. An orbital usually contains two electrons, and this quantum number helps us to differentiate the electrons found in the same orbital. Based on the Pauli exclusion principle that stated that no two electrons can have the same set of values for the four quantum numbers. So even electrons that lies within two electrons that lies within the same orbital would end up having different value for the spin quantum number. So now the spin quantum number is usually denoted by M subscript S and has two values, which is either plus half or minus half. So that these are usually the two values that we can have for the spin quantum number. So the plus half is the clockwise spin, while the minus half is the anti-clockwise spin. So this simply is the overview of the four quantum numbers that we have, and I want to believe that with this video you're able to understand the concept of the quantum numbers and how it helps us to determine specific information concerning electrons within the orbital. And lastly, as I end this video, we can also calculate the number of orbitals in a subshell. The number of orbitals in a subshell using the formula 2l plus 1, right? So we understand that we have shells, which are the energy levels. We have subshells, which is denoted by the azimuthal quantum number. Then we have orbitals that are contained in a shell, which ranges from 1 to higher numbers, right? Depending on the degeneracy of the orbital. So this degeneracy now can be calculated using the formula 2l plus 1. And then, of course, if we're able to use this formula to calculate the number of orbitals in a subshell now, that means we can also calculate the number of electrons in a subshell using the formula 2 into bracket 2l plus 1. This is because we understand that an orbital contains two electrons. So if the number of orbitals in a subshell is 2l plus 1, then that means the number of electrons in a subshell will be the product of 2 and 2l plus 1. I want to believe that is very clear. So to round up this video, if you have electronic configuration, let's say 3p2, 3p2. Now let's check this electronic configuration now and identify the various quantum numbers that we have in it. Now this 3 here is actually indicating the principal quantum number. So which means for 3p2 now, it is this electron 3p2 is contained in the third energy level. That's n equal to 3. That's shell M. K is 1, L is 2, M is 3. So this electron is contained in shell M, which is the third energy level. Then the P here now indicates the the orbital or the specific orbital now that owns or that is denoted by this electronic configuration. So remember we said for the azimuthal quantum number, when L is equal to 0, it is S. When L is equal to 1, it is P. So that means having this as P now, it is denoting the azimuthal quantum number, which is L equal to 1. So if L is equal to 1 now, from there we can also determine the degeneracy of the orbital now. We can determine the degeneracy of the orbital to be what? Plus 1, 0, minus 1. And then lastly, this superscript 2 shows the number of electrons that is contained in this particular orbital. So it shows that 2 electrons are actually contained in the orbital. And that is simply where I would round up for this video today. I want to believe you've learned one thing or the other. And if you have any question, do well to drop it in the comment section. If I find it, I would make a video of the